Right, today we are going to talk about mechanism of secretion of insulin from beta cells, right? What we are going to talk about that what is the mechanism, what are the molecular and cellular events which occur in the beta cells of the pancreas, right, during the secretion of insulin, right? Now first of all, I will tell you what is the most potent stimulus for release of insulin. The most potent and most powerful stimulus for release of insulin is, everyone knows, that is glucose. Now, first of all, I will tell you that how increasing blood glucose level makes the beta cells of pancreas to release insulin, and what are the molecular and cellular events, and then we will see the other factors. Let me draw a big beta cell, right? Let's suppose this is a beta cell of pancreas, right? Let's suppose this is a beta cell of pancreas. Here is the pancreas, you know, and you must be remembering from previous lecture. In the pancreas there are a lot of, what is there? Islets of Langerhans, usually 1 million to 2 million, right? And within the islets of Langerhans there are beta cells, and these beta cells are present in the center of the islets of Langerhans, like beautiful ladies, they are centered. And these beta cells, right, they are responsible to synthesize and release insulin to the circulatory system, right? But the question is that how beta cell know that blood glucose level is going up, and how increasing blood glucose level stimulates the release of insulin. Let me tell you from step. Let us suppose from gastrointestinal system, right, what is happening, that glucose is being absorbed. Glucose is coming to the circulatory system, and this glucose when come into circulatory system, now actually this glucose should enter into beta cell of pancreas to force the beta cell of pancreas to release insulin. Now, how the glucose will be transported inside the beta cell, right? There are special glucose transporters, right? There are special glucose transporter proteins, right? I will draw one transporter protein. It is 12 pass membrane, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. But anyway, this is not important for you to remember this is 12 pass. It is just, actually this is a glucose transporter, and this has a special type of domains where it can bind the glucose, right? And when glucose binds here, let's suppose here glucose binds. As soon as glucose binds, it flips in. It moves in and releases the glucose inside. Exactly. So again it is here, but when glucose is bound, what happens? It flips in, and when it flips in, glucose is released inside. Glucose is released inside, right? You see it's very happy, it has transported the glucose, right? Now, again after releasing the glucose in, it will flip back into this situation, and more glucose will bind and it will flip in. Now, this is a very special type of glucose transporter, right? This type of glucose transporter which is present on the beta cell, this is called glucose transporter type 2. What we call it? Glucose transporter type 2, or we simply call it GLUT-2. Is that right? Now, this GLUT-2 or glucose transporter type 2 which is present on the beta cell of pancreas, right, they allow the glucose to move in both direction. They allow the glucose to move from high concentration to low concentration. Is that right? And they very effectively take the glucose in. So when you have taken a carbohydrate meal, a lot of glucose is coming to the blood, and blood glucose level is going up. The rising blood glucose level lead to more activity of GLUT-2 transporters, right? And more glucose is entering into which cell? Beta cell of pancreas. Is that right? Now, this GLUT-2, it help in the glucose, right, to move along its concentration gradient. Of course, when you have, after taking the food, glucose concentration is more outside the cell and less inside the cell, so it will go down the concentration gradient, right, from outside to inside, and this movement or diffusion of glucose from high concentration to the low concentration inside is facilitated by GLUT-2 transporter. That is why this movement of glucose is said that there is facilitated diffusion of glucose, right, by the help of what? GLUT-2 transporter. Now remember, GLUT-2 transporters are also present in some other tissues. Let me tell you one thing. Right now, as I told you, that there are thousands and thousands of the GLUT-2 molecules present on the beta cell of pancreas taking the glucose in. So we can say that beta cells of pancreas, yes, what we can say? Beta cells of pancreas, right? Beta cells likes, yes, likes GLUT-2. Remember, 2 stand for two-way transport, right? Bidirectional transport. Now, beta cells like GLUT-2. Actually, this like should remind you that GLUT-2 are also present L for liver. They are also present in intestines, I for intestine, and there is no fun in telling you that K stands for kidneys. So what I am saying that basically when I say beta cells likes GLUT-2, it means that beta cells in the pancreas and liver, cells in the liver, cell in GIT mucosa, and cell in, yes, where? In renal tubules, right? All these cells have which kind of glucose transporters? GLUT-2. So again, if someone asked you that GLUT-2 transporters are present in which tissue, of course, number one is the beta cells. But beta cells likes GLUT-2. That is in liver, intestine, kidneys, right? All these tissues have GLUT-2. Now let's come back to the beta cell. When you have eaten the food, blood glucose level is going up, right? Then via the GLUT-2 more and more glucose is entering into cells. Now, how this glucose entry into cell will trigger the release of insulin, because in previous lecture we talked about that insulin is synthesized and stored in the beta cells, right? These are special vesicles, and in these vesicles insulin is stored. Let me make one large vesicle, right? So insulin is already present in this area in association with zinc. What is this? Zinc. This is zinc molecule, right? And with zinc molecule, there are 6 what? Insulin molecules attached. I will always make onward now insulin molecule like this. B chain, A chain, disulfide bond and disulfide bond. So this is insulin. So there are 2 insulin. What is this? 2 insulin attached here, 2 insulin molecules here, 2 insulin molecules here, 2 insulin molecules here, and 2 insulin molecule here. Now, it means that there are 6 molecules of insulin precipitated or attached with the zinc molecule, and this is called hexamer of insulin. So we say that insulin is stored in the secretory vesicle in hexameric form. But remember, once insulin is secreted in the blood, it can be present in dimeric form or monomeric form. But the biological active, fully active form of insulin is monomeric. Now let's come back. Now we have to develop the molecular events that entry of glucose. Listen, entry of glucose in beta cell should trigger the release of insulin. What happens in between? How entry of glucose forces the insulin to be secreted? Let me tell you the mechanism. Actually, when glucose enter in the beta cell there is a special enzyme, right? We call it, this enzyme is called glucokinase, right? What is it? Glucokinase. This glucokinase enzyme, right, it is very, very active in phosphorylation of glucose. What I mean by phosphorylation of glucose, that glucokinase present in these beta cells, whatever glucose is entering in, it will convert that glucose into glucose 6-phosphate. It means this enzyme will phosphorylate the glucose. You know why it is important to phosphorylate? I told you these transporters are two-way, right? If glucose enter, it can escape out. Is that right? Especially it can escape out if outside insulin, if outside glucose level go down. But actually, when glucose comes in and glucokinase work on it and add a phosphate with the glucose at 6th position, 6th carbon, and convert the glucose into glucose 6-phosphate, phosphate is so much charged that it cannot pass through membrane and it cannot go out through a what? Transporter. So once glucose convert into glucose 6-phosphate form, it is trapped inside the beta cell, right? So you see, as soon as glucose enter in, we put a chain into its leg. This chain is what? Phosphate. What is this chain? Phosphate. Once this glucose has been chained, now this cell will do something nasty thing with this glucose. You know what it will do? It will take this glucose 6-phosphate into the pathway of glycolysis. In the pathway of glycolysis, right? And this glycolysis will end up in formation of what? Pyruvic acid. It will convert into pyruvic acid or pyruvate. And this pyruvic acid will enter into mitochondria. Let me draw one mitochondria here, right? This is mitochondria. Now, this pyruvic acid, right, will be eventually transported into mitochondria, and there, this will pass through two processes. Number one, TCA cycle, and secondly, oxidative phosphorylation. Oxidative phosphorylation, right? Now, it means once glucose entered in, glucokinase converted into glucose 6-phosphate, which went through the glycolysis pathway, and pyruvic acid enter into mitochondria, and there it passes through what? TCA or Krebs cycle, and then oxidative phosphorylation occur, and during all this, the energy which is produced, that energy is used to convert, yes, that is very important, that energy is used to convert ADP into, yes, ATP. So it means when more glucose is coming into these cells, when you have taken the food, more glucose is absorbed from GIT, blood glucose level is going up, more glucose is transported into the cell, and glycolysis become more active, and TCA cycle and oxidative phosphorylation lead to conversion of more ADP into ATP. So intracellular level of ATP will go up, and of course intracellular level of ADP will go down, right? Now I still did not tell you how the entry of glucose is going to release insulin, but I'm moving towards that. By now you know that as more and more glucose enter into cell, inside the beta cell ATP level goes up. Is that right? Let's stop the story here. I will tell you another part of the story. There are special type of channels, potassium channels present in the beta cells, right? I will draw it here. This is a very special type of potassium channel, right? This is a very special type of potassium channels which are present in the membranes of cell membranes of beta cell, right? Now these potassium channels, right, are normally open, right? Normally they are open. This is a special regulatory unit here, right? And here, okay, I will explain why it is some shape like this, but for a while you just trust me that actually if this move down, channel will close, if it move up, channel will open, right? And who is sitting here? ADP. Who is sitting here? ADP. When ADP is sitting here, yeah, it's low energy, angry. But when ADP bind with this channel, what really happens? This channel is open, and when channel is normally, when channel is open, it allows the potassium to escape out. What is this? This is potassium ions, and as you know, potassium, intracellular potassium levels are high. So under its concentration gradient, potassium moves out of cell. So basically, resting membrane of beta cell are normally constantly losing potassium outside. When they are constantly losing potassium outside, loss of positive ions outside develops intracellular negativity. Again, let me tell you. When inside of the membrane is losing positive ions outside, so inside become deficient in positive ion as compared to the outside of the membrane. It means inside of the membrane become electronegative. Usually, it remains electronegative of about minus 70 millivolt, right? Resting beta cell, right? And what happens now? You come over here. Glucose came in, right? Resulted into conversion of more and more ADP into ATP. When ATP level become high, right? What will happen? It will try, the high energy molecule of ATP will love to play with this channel. Now, this ADP is becoming less, am I right? Yes. So, it will dissociate from here, and this is the point where ATP likes to bind. And when ATP will bind here, what will happen? When more glucose is entering into cell is having more intracellular ATP, and when cell has more ATP, what really happens? Right? It's very simple that now ATP will sit at this point. This ATP will attach here, and when ATP will attach here and ADP will dissociate and ATP will associate, what will happen? That it will become like this. And who is sitting here? What is this molecule? ATP, right? Or, okay, I'll make it more simple. What is the tide here? ATP. Now, when more and more ATP, listen now very carefully. When more and more glucose enter into cell, more and more ATP is generated. This ATP bind with which channels? Potassium channel. That is why these potassium channels are called ATP sensitive potassium channel, or we can also call it ATP regulated potassium channel, right? So this ATP, when it binds here, then what happens? These channels are closed, inhibited. When potassium channels in this membrane is inhibited, right? Can now potassium go out? No. Now potassium is blocked in. Now potassium is blocked in. Potassium cannot go out. It means now cell start retaining positive ions. Previously cell was constantly losing the potassium, right? Now if the cell is retaining potassium, is that right? Because of ATP has closed the potassium channel. When positive ions are kept within the cell, or these are retained in the cell, right? Do you think we can keep it minus 70? No, because what will retain in, that will neutralize somewhat of negative degree. So when more and more potassium is retained in, it will become minus 70 will convert into minus 65. When more positive ions are laid, it will become minus 60. Then it will become minus 50. Why? Because this retained positive cations, potassium, is neutralizing or cancelling the intracellular negative, right? Now, before glucose entered, before ATP was there, when there was no ATP in the cell, channel was in this operating form, and more cation was going out, and membrane was too much negative. So in this situation, when membrane was in this situation, we say membrane is polarized negatively. What we say?
Polarized
Negative is, membrane is polarized negatively. But when glucose come in, intracellular ATP levels goes up and ATP sensitive potassium channels are blocked, and now potassium cannot go out, and this retained potassium, right, cannot allow the intracellular membrane to remain polarized negatively. So some of electronegativity is neutralized and this cell membrane become less negative. Rather than minus 70, after this blockage of the channel, it become, let's suppose, minus 50 millivolt. It means now this membrane has lost some of its negative polarity. Membrane has lost some of its negative polarity, or we can say membrane is depolarized. What we say? Membrane is depolarized. So basically, when ATP sensitive potassium channels are closed, right, membrane becomes depolarized. It becomes less electronegative. When membrane channel, membrane voltage become minus 50 millivolt, and other event occur. What is that? Change in the calcium channel. Actually, there is another type of channel in these cells. You see, life is not simple. Even beta cell is not simple. Now look, here is, what is this channel? This is calcium channel, and this calcium channel is called, voltage sensitive calcium channel. Which calcium channel? Voltage sensitive calcium channel. Now when membrane is fully polarized, that is minus 70 millivolt, at this voltage, this calcium channel is closed. This calcium channel is closed, right? It means this calcium channel is sensitive to, what is this? Voltage. When membrane is fully polarized, right, it remains closed. But as soon as membrane becomes somewhat depolarized, right, this channel can sense the change in voltage, right, and when membrane becomes depolarized, this depolarization sensitive calcium channel open. What channel open? Sensitive calcium channels open, right? So we call this calcium channel, right, this calcium channel remain closed. This calcium channel remain closed when cell is negatively polarized or at resting membrane potential. But as soon as when glucose enter in, ATP level goes up, right, ATP sensitive potassium channels close and retained potassium depolarizes the membrane, right, then this voltage sensitive calcium channel or depolarization sensitive calcium channel open, and as soon as it open, calcium will move from high concentration to low concentration, and you must know that extracellular calcium levels are very high normally as compared to cytosolic calcium channel. So as soon as calcium channels open, what happen? Extracellular calcium, right, it start moving in, and when this calcium is moving in, right, intracellular calcium levels go up. Is that right? And this intracellular calcium channel, this intracellular calcium, right, when its concentration goes up, it stimulate secretory vesicles and move this secretory vesicle, right, towards the cell membrane, and yes, this increased intracellular calcium moves these, what is this, secretory vesicle towards the cell membrane and fuse them, and when they fuse, what comes out? Now you can tell me what will come out. Yes, a good doctor will tell me insulin, number one. What else will come out? C-peptide, right? Insulin, I told you, I can draw it like this. Insulin will come out. Number two, what else will come out? C-peptide. And a very good doctor will know that another thing called amylin will come out, and a very little pro-insulin which was not yet converted into insulin and what is this? C-peptide, right? But out of this, at this moment, we'll just remember insulin and C-peptide. So, this is the increasing intracellular calcium level which help the secretory vesicle to secrete or release its content to the extracellular fluid and eventually to the circulation. Most important content here is insulin molecules and what is this? C-peptide. Is that right? We'll talk about the importance of C-peptide later, and we'll also talk about biological actions of insulin later, right? But this is the molecular mechanisms which are involved in release of what? In release of insulin, secretion of insulin. The master regulator of insulin secretion is rising blood glucose level, right? Let me make it a fast review, and then we'll talk about the clinical points related with this mechanism. What we are going to discuss now, the molecular and cellular events, right? Molecular and cellular event during which lead to the release of insulin on arrival of glucose. Again, you have taken the food, right? Blood glucose level is going up. The glucose enter into these cells by, now you will tell me, by GLUT-2 transporter 2. When more and more glucose enter in, glucokinase enzyme work on this glucose and convert it into glucose 6-phosphate. Here I want to tell you one thing. Glucokinase is the rate limiting step in all these molecular events, right? So we can say beta cells are sensors of, they are glucose sensors, they can sense the glucose. But more truly speaking, more specifically speaking, this is a glucokinase in beta cells which is glucose sensor, right? It is the rate limiting step, right? So more glucose enter in, more glucose convert into glucose 6-phosphate, more glycolysis occur, and more pyruvic acid is available to enter into TCA cycle and oxidative phosphorylation system, eventually convert more and more ADP into more ATP, right? As ATP levels in the cells are going down and ATP levels are going up, then ATP bind with what? Potassium channels, and ATP-sensitive potassium channels are inhibited. When potassium channels are inhibited, right, what really happens? That potassium is retained in, and when there is decreased outflux of potassium, this retained potassium will make the membrane less negatively polarized. So minus 70, it may move to minus 60, minus 55, minus 50, minus 45. So in a way, membrane is losing its minus negative polarity due to decreased outflux of potassium. And when membrane is depolarized, right, or it becomes less negative, then voltage sensitive calcium channels open and extracellular calcium enter into cytosol, and when intracellular calcium levels goes up, this rising calcium level stimulate the fusion of secretory granules which are storing the insulin, preformed insulin, which is present here in association with zinc as hexamers, right? This rising level of calcium fuses these storage vesicles with the cell membrane, and content of these storage vesicles are released outside the cells, and later on these content go to the blood right through the fenestrated capillaries in the islet of Langerhans. The main contents are insulin and C-peptide, which are released into circulation in equimolar amount, but there is a very little amount of amylin and very little amount of proinsulin also. We will discuss biological actions of insulin later, and we will also discuss the importance of C-peptide level in the blood later. But I would like to discuss some clinical points which are related with this whole mechanism, right? Some important points. For example, number one, in some people, this glucokinase enzyme is mutant. If glucokinase enzyme is mutant, you can see it, it is very sad, it is not functioning well, right? It's weeping and it is sitting here in a very sad fashion. We can say that this is mutant what? Glucokinase. If glucokinase is mutant and it has some loss of function, it does not function well, do you think then it can take the glucose into glucose 6 phosphate rapidly? No. So what happens in these patients? Now listen carefully. If someone glucokinase is mutant and it is not properly converting the glucose into glucose 6 phosphate product, what will happen to this person? That even if a lot of glucose enter here, there will be less amount of glucose 6 phosphate, there will be less conversion of ADP into ATP, there will be less inhibition of potassium channel, and if there is less inhibition of potassium channel, then the potassium still keep on going out. In spite of the fact glucose has entered into cell, still some potassium keep on leaking out, and membrane does not depolarize properly, and calcium channels do not open, and enough calcium does not come inside the cell, and then enough insulin is not secreted. It means those people who have mutant glucose kinase enzyme in the beta cell with loss of function or partial loss of function, they cannot secrete the insulin effectively. So these patients may have lot of stored insulin, but secretion of insulin in response to rising blood glucose is very poor. If there is less insulin going to the circulation, then what will happen? That glucose cannot be, this insulin deficiency will lead to diabetes mellitus, chronic hyperglycemia. This type of diabetes mellitus, which occurs due to dysfunction of glucokinase, right? This type of diabetes mellitus clinically is like type 2 diabetes mellitus, but it occurs in very young patients, right? You must be knowing that type 2 diabetes occurs in older patients, but this type of type 2 diabetes occur in very young patients. So we call it that these patients suffer with what we say MODY. I don't say these patients are moody. MODY means there is maturity onset diabetes of young people. What is this? Again, MODY stands for what? MODY. Maturity onset, because type 2 diabetes is usually in mature age. So we say there is maturity onset diabetes mellitus, maturity onset diabetes mellitus of young people, young patient. Is that right? So this is one clinical point which is related with this molecular pathway, that glucokinase is extremely important, and in all of you glucokinase in beta cell should be efficiently converting glucose into glucose 6 phosphate so that more ATP is produced, and whenever glucose level go up, there is more ATP in the cell and you can secrete more insulin, right? Am I clear? Yes. Okay. Second clinical importance, yes, another important thing. There are some drugs, right? Let's hypothetically talk. If we have a drug which can bind here and close the potassium channel, it will be a very useful drug. For example, let me tell you, if we put a drug here, right, and this drug is sitting here very happily, right, and keeping these channels off, inhibited, this will be very useful drug. You know why? Because if we have some drugs which can bind with the potassium channel and inhibit them, they bind the way ATP bind. So we can say some pharmacological agents can bind with these ATP-sensitive potassium channels and block them. Is that right? And if they are blocked, then membrane will be more effectively depolarized, more effectively calcium will enter in, and more effectively insulin will be secreted. So such drugs can be used, right, to increase the insulin secretion by the beta cells of pancreas, right? So we can say these drugs are potassium channel, yes, what are they? Potassium channel blocker. What are these drugs? These are potassium channel blocker, yes. Now, so potassium channel, which potassium channel? Voltage sensitive potassium channels present on the beta. I'm stop it. It is not voltage sensitive. It is ATP sensitive. Yes. Why you didn't correct me? ATP sensitive potassium channels in the beta cell of pancreas, if they are blocked by the drugs, then the beta cells will be more rapidly depolarized and they will release more and more insulin, right? Now, so it means these drugs can act as secretagogue for insulin. They can force the cell to release insulin, right? And such a drug can be useful in type 2 diabetes mellitus. Remember, in type 1 diabetes mellitus, most of the beta cells are destroyed. So such drugs cannot work well, right? But in type 2 diabetes mellitus, there are enough beta cells in the pancreas, right? But if you give such a drug, these beta cells can be forced to release more insulin, right? Now, can you tell me some drug which are, yes, can you tell me the name of some drugs or groups of some drugs which can inhibit the ATP sensitive potassium channels in beta cells of pancreas? Yes, who will tell me? No one. Yes, Socrates. Yeah, sulfonylureas, excellent. One group of drug is sulfonylureas. You know, these are oral hypoglycemic agents which are used in type 2 diabetes. I will mention two drugs out of this sulfonylurea. One is tolbutamide, and other is glyburide. But there are many other also. And these sulfonylureas, they actually, what is the mechanism of action of sulfonylurea? Oral hypoglycemic sulfonylurea bind with the ATP sensitive potassium channels and block them, right? And keep the beta cell membranes depolarized. And excessive amount of calcium come in, which forces lot of insulin to go out, and this extra amount of insulin which goes into blood, right, it will act on the high glucose level and push the glucose into liver and adipocytes and muscles and bring the glucose level down. That is why they are called, because they are taken orally, oral hypoglycemic agent. And other group of drugs are also available which also work here, right? And that group of drug is basically, who will tell me the name of the second group of drug which also work on the ATP sensitive potassium channels and block them? One group is sulfonylurea like tolbutamide and glyburide, and second is meglitinides. Very good. The second group is, which is a new group of drugs, meglitinides. These meglitinides, right, they also work in the same fashion as sulfonylurea work, right? Both of this group of drugs, they basically inhibit the potassium, ATP sensitive potassium channels in beta cell, right? Meglitinide examples are repaglinide or nateglinide. Repa, R-E-P-A, it is not rape, repaglinide, this is repaglinide and nateglinide, right? So here what we understood, that if you give patients sulfonylureas or you give meglitinides, these channels will be closed, membranes will be more easily depolarized, more calcium will come in, more insulin will be released, and this insulin will bring the blood glucose level down. So they act as a hypoglycemic agent. Now I will talk about one more drug here. There is another drug which can act on these ATP sensitive potassium channels, but that work in a different way. Let me tell you how that drug works, right? Again I will make, what is this? Potassium channel, right? And this drug which I am going to talk, that basically is not working like binding like ATP, rather it binds at a different domain, Because this binds, this drug sits over here. Yes, and it will bind where ADP bind and keep this channel permanently open, right? So this is actually potassium channel activator. What this drug is doing? It is not binding here to close the channel, it is binding at different point, right, and keeping the channel excessively open, right? And this drug which is keeping the channel excessively open, right, that will lead to excessive loss of potassium, and this excessive loss of potassium will keep the membrane very, very negative. So membrane become extremely negative, not minus 70, maybe minus 80 millivolt or more. So we can say this group of drug or this type of drug bind with the ATP sensitive potassium channels in such a way that it keeps the channel open excessively and lead to excessive loss of potassium and keep the membrane very much hyperpolarized. And if membranes become hyperpolarized, can they easily depolarize? No. Can they bring the calcium in? No. Can they secrete the insulin? No. So actually this is a activator of ATP sensitive potassium channel, but actually this inhibits the secretion of insulin because membrane is too much negative, too much hyperpolarized, right? And it cannot be depolarized easily, and calcium cannot come inside easily. So calcium, voltage sensitive calcium channel do not open and insulin is not secreted. So they inhibit the insulin secretion, right? And when insulin secretion is inhibited, blood glucose level can go up. So such drug can work as hyperglycemic agent. The classical example of this drug is, who can tell me? Yes.
Diazoxide.
Very good. Diazoxide, right? Diazoxide. So diazoxide is a drug which can act where? Yes, it can act on ATP sensitive what? Potassium channel, keep them overactivated, lead to excessive loss of potassium, efflux of potassium, keep the membrane hyperpolarized, does not allow the membrane to depolarize, do not allow the activation of voltage sensitive calcium channel, do not allow the calcium to come in, do not allow the insulin secretion. This drug can be used in a very special situation. You know, some people develop, unfortunately, a tumor of a neoplasm of the beta cell. That is called Insulinoma. What is that called? Tumor of beta cells, where a lot of beta cells are neoplastic in the pancreas, and this is called insulinoma. In the patient with insulinoma, there is excessive beta cells and they release too much insulin. They are secreting too much insulin. And if excessive amount of insulin is present in the blood, too much insulin is present in the blood, that will take the blood glucose level down, and these patients will have severe hypoglycemia. Again, let me tell you, if you come across a patient who have insulinoma, what will happen? That cells of insulinoma will secrete excessive amount of insulin, and this excessive amount of insulin will take the blood glucose level down and produce what? Hypoglycemia, right? In such patient, you can give them diazoxide, so that diazoxide goes and keep the potassium channels open like this, and so right, what will happen? Excessive potassium will come out, right? And these cells cannot be depolarized and calcium cannot enter into these cells and insulin cannot be secreted. And in this way, you prevent the insulin secretion by the insulinoma cells, and you reduce the tendency of hypoglycemia. Is that right? Do you have any question up to this? Okay.